Okay, welcome everyone. Today, Jeremy, Mr. Attention. We're going to talk about 11.1 differential equations. I'm just going to work a couple of examples, and then I'm going to um, give you a little quick intro to 11.2. So this is kind of 11.1 and 11.2. So you've all read the differential equation stuff, and you know that a differential equation just involves some kind of an x and a derivative of y typically, or a second derivative of y. If it involves a second derivative of y, then it's called a second order differential equation. Johnny yesterday had looked at number 3. And what does number 3 say in 11.1? Okay. Right, and then and we worked this yesterday, and both of us felt like soiled a little bit. I don't know. We just didn't feel very good about it. But I haven't been able to come up with anything better. Is this a solution? And the only thing that I came up with, and Mr. Hale, maybe you can find something better, is to take the first derivative um, of this. So dy dx equals what? Hey, Ben. Sure. Um, what's the first derivative of this? Yeah, that's 3x squared. And I chose to do that because I saw a first derivative here, and I know I can substitute in. And this is the only way I saw it. So then I can take this. I can take this. Yeah, Jeremy sees it already, and substitute in 3x squared minus, well, 3y. I don't think so. And then we got, wait, oh, not 3, not 3, just x cubed. I saw that one even before you did. Okay, no, I had 3x cubed on the brain. And so you get 3x cubed minus 3x cubed equals 0, and then you could get 3x cubed equals 3x cubed. And at this point, you say to yourself, well, is this true for all x? Is this true? It's the same, so you say, thus it's proven, you know. And I know that doesn't feel very good, but I think in this case that's about all you're going to get. So, I don't know. Well, I don't know. Both Johnny and I yesterday were kind of like, really? Mr. Hale, do you see anything better? Right. And substitute in. So even though that doesn't feel very good, it doesn't feel like a proof, but, you know, it's probably okay. And then I looked at number 7 this morning. Even though that's not assigned, I thought, boy, that's a tough problem. That's good. So what does number 7 say? Check it out, 11.1, number 7. Y equals A plus C. Yes. Yeah. Yeah, this one's a little bit of pucker factor. It's yeah. So once again, I start with y equals a plus some constant e raised to the kt power, and I want to take the derivative of that. Okay, so dy dt of that is going to be what? Great question. Is a constant? Alex? Yes, a is a constant. It's not t, because notice I wrote this in Leibnizian notation. The derivative of y with respect to t. So everything else is a constant. A is a constant, c is a constant. So we're not going to stress about them. So what's the derivative of a constant, Jacob? Derivative, not integral. Good man. Good Paul. You're about to panic, but you got it. Good job. Okay, so we got 0 plus. Okay, that C is messing with you. Let's think about it like this. What about if I wrote this as dy dt of A plus dy dt of C e to the kt? Then what would you do? Can you do this? Yes, you can do that. And the reason I would do that, and I know this seems like an oversimplification, but then you're only focusing on what's really important here. C is not really important. I mean, it's a scalar multiplier, but who cares? You know. Okay, 0 plus C times. Okay, now what about e to the kt? That's money. You do. So e to the kt times. No. Think about it. Tom? Oh, no. Well, you do chain rule, but you're applying it not totally. Remember, it's e to the kt, whatever's here, times what? Times k. Good, good. Well, this is 0 plus. And that's why I pulled the constant out here. Okay. So this was 0 all alone. That's one item that we look at. Plus c times this. And if this were c plus this, then it'd be another 0. But this part right here is not 0. It's a good question. Hello, Moana. Okay. So then, and Mo, I've been recording this if you want to watch the part that you missed. Okay. Yeah. Yeah. Okay. And then, so we've got dy dt equals c e to the kt times k. Now here's where it gets tricky. No, it doesn't look like what we want it to look like. We want it to look like something, with an A in it. And we don't have any A's. Okay, so we need an A term. We do, and that's going to help us. That is going to help us big time. Okay, so we're going to need some big time A terms. So check this move out, and you're going to go, no, that's not cool. That's not fair. So we got dy dt equals k times the quantity c e to the kt. Here, wait for it. Yes. I know. We'll get an A term. Okay, you're right, Mo. Oh, hang on. No. We're going to need it. Only the derivative. So then we're saying dy dt equals. I know it's very weird, and it's not something you'd think of off the top of your head. Okay. Okay. Well, carry that through and see if it works. Okay. And it may, and as I've said many times, there's more than one way to get it, and visualize the way you see it. So notice the way I grouped this. I put c e to the kt plus a in one group. Why did I do that? Because that equals y from way back in the day. Y equals c e to the kt plus a, right there. Okay, so you were just looking at it from a slightly different perspective. And again, I see things a little differently maybe than, whoa, it might finally be breaking. I don't know. I see things maybe a little differently, but if you see it that way and it works legitimately and you can demonstrate it on a quiz, right on, man. Okay, so then we get dy dt equals k times y minus a. Oh, haha, yes, it is what we want. Okay. And so that works. So, Jeremy, you said what? Back here, you said, oh, you said, right. Okay, so you said subtract A up there. Okay. Right. And that works, although some people in proofs are really down on that. They want you to leave what you started with untouched and finish with that. I don't know. Have you encountered that much with professors? Exactly that. Sometimes they'll, yeah. Right. Right. So anyway, Jeremy, what he's saying is if you subtract A from both sides, you're proving something slightly differently, and that the whole idea is that I would give you full credit, but you want to be able to say exactly this is true, not any kind of altered form, and then you would use that in subsequent proofs. And yeah, some people get really particular about it, but I would have given you full credit for your method. Questions on that? Okay, I've got one more. Tom? Okay. Okay. I have one more, and then I'll get you going. Because I think you'll like the cards. You've done the cards before, but I've got a new set today. This is also an 11-1, number 10. It says, Jacob, hang in there. I'm almost done. Fine. You know, Moana showed up late, so she wants to catch up, not visit. Find the values of, what's that funky W called, Mr. Hale? No, it's not omega. It's a funky Greek W. I thought omega was, is it lowercase omega? Okay, that's uppercase omega. So lowercase omega, for which y equals cosine t omega t satisfies a second order differential equation. Okay, now let's talk about order. So we've had forever dy dt, right? So then what if you take the derivative of that with respect to t? And I hate this notation, but your book uses it. So, no. Yeah, they use d to y. Oh, I hate this notation. dt. Ah! Well, it's not really squared either. It's just notation. It's just saying the second derivative of y with respect to t. But they do it like it's multiplying, like you're going dt times dt, which is dt squared. Ugh. Well, but it's not. I don't know. I hate that notation, but you see it a lot. It's really, it reminds me of like this. It's just faster. I hate this notation too, but you see it all the time. So anyway, a word of warning. It's ugly notation, but you see it all the time. So this is the second derivative of y with respect to t. And you'll see this in a second order differential equation. So number 10 says find the values of omega for which y equals cosine omega t satisfy the second order differential equation. Equals 9y, oh, plus 9y, sorry. Plus 9y equals 0. And this is number 10 in your book. Okay, so if y equals cosine omega t, what does dy dt equal? Cosine omega... Oh, yeah. Well, double check. Am I right on that? Look at number 10. Which one's right? Right here? Okay, so good. I want to clarify that. So it's cosine omega t. Okay, thank you. Yes. Well, as you all know, I make lots of little mistakes, and I beg your indulgence, but I also need your help finding them. So, okay, here we go. If y equals cosine omega t, what does dy dt equal? Negative sine omega t, lowercase omega, times what? No. Times. times omega. Yes. Okay. And yeah, typically they'll write that opposite of omega sine omega t. Typically that's what you'll see. Okay. Oh, you're crazy, Jeremy. Why would you want to do it again? We don't really want to, but we will. Let's do it again. So that is the derivative with respect to t of the opposite of omega sine omega t equals and maybe it'd be easier to do it like we did right here. Maybe that's easier to see. Let's do that. I think that's easier to see. Okay, let's go opposite of sine omega t omega. Equals, what do you got, Alex? Omega ohm omega squared. Anytime, guys. Perfect. Alex was, oh, really? You got it. Exactly. Okay. And typically, again, you'll see this as opposite of omega squared cosine omega t. Okay? So now, before we had, remember, I'm going to go another color. We had second derivative with respect to t plus 9y equals 0. Okay, let's go crazy. What are we going to do? Yes. What's it going to be? Plus 9 times cosine omega t equals 0. Good. Jeremy, you are so no fun. No fun. All right, let's solve it for real. He's right. Close, not divide. Think think of this as all being inside some kind of. Thank you. Cosine omega t exists in both terms. Therefore, let's factor it out, not cancel it or subtract it or whatever. Very good, Mo. Not bad for a late kid. Man, equals 0. Okay, so what does that mean? Means 9 minus omega squared equals 0, or what about omega squared? What could it equal? Well, yeah, negative omega squared would equal negative 9, so omega squared would equal 9. So Jeremy's right. Yeah, but if cosine omega t equals 0, what does that mean? We don't know what t is, so let's just stick with this. Right. So omega w, you got me doing it, equals plus or minus 3. Yeah. So that's pretty cool. Right. Right. They ran out. I think there's 24 Greek letters. If you use uppercase and lowercase, you can get more. Okay, now, how many have read, I guess I should say first, questions on this? And this is online if you, or will be online tonight if you want to view it. How many have read, or I guess I should say, how many, no, I shouldn't do that. How many have read 12.2? Just, what is it? 11.2. We're in 12 in trigonometry, and it's messing with my mind. You looked at it. So slope fields are a new concept. Slope fields, they're like slope diagrams, basically. Okay? If you haven't done it, that's fine. And I'm going to throw this on. Let's say we have a differential equation, dy dx equals 2x. And this is in your book, but I liked it, so I'm going to use it. Normally, I don't talk about ones that are in your book, but I like this one a lot, so I'm going to use it. Dy dx equals 2x. What is that saying? What is that saying if you have some kind of a diagram? It is. Changing y over changing x equals 2x. So, yeah, it's got a slope of 2x. So let's put a bunch of numbers in here just to try it out. X, and then instead of, and then over here we can say dy dx. And so let's go like -3, -2, -1, 0, 1, 2, 3, whatever. So -6, -4, -2, 0, 2, 4, 3. Kind of have it. 4, 6. So hang on. Don't fish give. Man. Slow down. So let's start with the easy one. At 0, what are these slopes going to look like? They're going to be horizontal. The slopes, and we don't know where the function is, and we don't care. The slopes are going to be horizontal. At -1, what are the slopes like? So I'm here at -1. What are the slopes like? -2. So everywhere, if you draw a vertical line everywhere here, the slopes are going to be -2. At -2, what are they like? -4, so they're steeper. Exactly, exactly. It's a way to solve differential equations graphically. It's what it is. Well, and you know one thing I like about it? It drives home that plus C concept that is so important. And too bad Derek, who won't watch this video, is not here. Exactly. C is which one, it determines which one you use. Okay? Now, let's think about this. Johnny, the fish giver, Pesca Johnny. Anyway, Johnny looked at this and said, oh, it's a parabola. Well, in fact, it's a whole family of parabolas. He's right. But look at the slope. Okay. Yeah, kind of. So, but here's what's really neat. Okay, dy dx equals 2x. What about the original function y? What would y equal? Okay, that's fair. Equals the integral of dy dx. So y equals the antiderivative, the indefinite integral in this case, of 2x dx, thank you. So then y equals 2x squared over 2. Thank you, Mo. So y equals x squared. Now look. Look at the purple lines here. So it's beautiful. Plus c. Okay? And look, all of these make that a true statement. All of these parabolas. So you don't know where they're at. Okay? But that's a parabola. And its derivative, dy dx, is we go from a second degree polynomial, parabola, to a first degree polynomial for the derivative, a line, which we talked about last spring, or this is the spring, last fall. Okay? And I thought that's pretty cool. Mo, what are you happy about? It is. It is indeed. Okay. I'm going to quit now and hand out some cards for you to practice.